So thank you for the introduction. So my name is Andreas. It was supposed that we have the talk together with a colleague, Michael. He's not here, actually. And so I will give the talk alone. And that means that I will leave out some very detailed content at the end. I'm working at the German Aerospace Center in the Simulation and Software Technology Division. So I'm working with software, writing software. My personal background, I have a degree in mathematics, in industrial mathematics, and I'm working at the Aerospace Center since 1989. And what I'm talking about is basically space debris and a software that we are developing for like cataloging and analyzing space debris data. But who are we? The German Aerospace Center. I think most of you are here from the US and don't know the DLR, the German Aerospace Center. But I think most of you know NASA. And if you know NASA, I mean, we are more or less the same, but a little bit smaller. I think we have 8,000 people, and NASA has, I think, more than 30,000 people. But the fields of research and the fields of working are more or less the same. So actually, the guy over there, this nice selfie, is my former boss. He was in space 1 year. We took 6 months on the Russian space station and 6 months on the ISS. And he's a really cool guy. It's very nice. And as I said, I'm working in the Simulation and Software Technology Division, and we do research and development in the field of software, distributed systems, software engineering, and high-performance computing. And, well, the next section is a bit critical because I'm not an aerospace engineer or something, and I'm a mathematician, and I'm trying to talk about space debris. So what is space debris? The first thing that we have to talk about is the space itself. I mean, this thing, I know you know this thing. This is the Earth. We are living there. And most of our life is happening on the surface. But another part of our life is happening in 2 areas around the Earth. So there's like the lower orbit, 300 kilometers up to 2,000 kilometers. A lot of satellites and other stuff is flying around there. And the geostationary orbit, which is around 36,000 kilometers. Most of the communication satellites are located in the geostationary orbit. So a lot of space flight is going on, targeting these orbits, rocket launches and satellite, the space station, of course, satellites for Earth observation, communication, telescopes, and so on. So currently in use is the Kepler telescope of NASA, which tries to find a second Earth or something. And I think they found a couple of interesting places where you have to go, but, well, it takes too long to go there, actually. But we have a lot of time in the future. So the space travel is not very odd. Like we do space traveling 50 years or so. And all the mankind has launched about 5,000 rockets. It's not clear. This number is not really precise. We don't know really how much rockets did the Russians actually start, or the Chinese, and so on. But around 5,000 rockets. We have placed around 6,000 satellites in orbit, and 1,000 of them are actually currently active, that we're using for communication and other stuff, and espionage and so on. And there's also a lot of space debris. Space debris is, or space waste, or something like that, is defunct objects in space, maybe satellites that are no longer used, or rocket stages, fragments from explosions and collisions, released objects, like there were actually astronauts who lost, well, tools after repairing things. Yeah? Slack of solid fuel rockets, and, well, other sources. I don't know what that is. And the number of space debris objects in space is increasing. This is the number, these are the numbers from 1985 to 2012. And you can see it's increasing, and especially at the end, there are two steep steps. And these are special events. The first is in January 2007, there was a Chinese satellite that was hit by a Chinese rocket. They tried to destroy their own satellites as was some kind of, well, let's say, military experiment. And this increases the number of space debris objects from around 4,000 to 7,000, 8,000 objects. And another incident was the collision, an unplanned collision of two satellites, Iridium, and this is, I think, a Canadian communication satellite, and Cosmos, a Russian satellite. They collided, and this leads to more than 2,000 additional space debris objects in space. So one collision in space leads to very, very huge increase in space debris objects. Oops, sorry. As you can see, the impact of this with these two pictures of these two incidents. The space debris of the Chinese satellite just 1 month after the disintegration, and the space debris of the two collided satellites just 50 minutes after the collision. There's a lot of stuff flying around after these incidents. And we have catalogs and databases for storing information about space debris data. Well, current catalogs have about 16,000 objects from a size larger than 30 centimeters or so. But actually in space there are much smaller objects. There are at least about 30,000 objects which are larger than 10 centimeters, and there are 750,000 objects larger than 1 centimeter, these small objects. And there are 150 million objects which are larger than 1 millimeter, and probably many, many more objects smaller than 1 millimeter. But what is the impact of these objects? Why we have to deal with space debris? Is this important or not? So in the laboratory, you can make an experiment. You can shoot with a small 1 centimeter aluminum sphere into an aluminum block, which has about 10 centimeters, and you can see the impact of this. And you can imagine what happens if such a small sphere hits the International Space Station or other important things. And a real impact in space is this. This is a solar panel of a satellite which was hit by a space debris object. And I think we don't know the exact size of this space debris, but this causes the damage. And also the space station was hit by a couple of objects in the previous years, but not very large objects. I'm coming to that. And the distribution in different altitudes from Earth are very different. So this is from 200 kilometers to 2,000 kilometers. And you can see, the interesting spaces are about 400 kilometers. This is where the ISS lives. There are not too many space debris objects. A little bit higher is satellites like a Terrasar. This is one of our radar satellites. And most of the satellites are in the region 700 to 800 kilometers. And also this is naturally the region where the most space debris objects are, because there were previously the most satellites. Yeah, why is this important to deal with space debris? Well, we want to predict collisions, of course. For the space station or the manned space flight, it's important to predict probable collision. And yeah, for the space station, this happens every couple of months or weeks. Actually, this was 2 weeks ago, July the 16th. The crew of the ISS has to leave the ISS, and they went to the Russian Soyuz module because there was a space debris particle crossing the way of the ISS. And well, actually, I don't know, they were at the Soyuz a couple of hours, and then they went back to the ISS because the space debris particle don't hit the ISS. And yeah, actually, just when I was sitting in the back a couple of minutes ago, I found this news message from this morning, like 5 or 6 hours ago. There was another space debris particle crossing the way of the ISS, and so the Russian commander, they made a maneuver to I don't know actually what they did. They can actually fly higher or lower with the ISS to avoid hitting the space debris particle. And as you can see, these things happen like every second week or so. Yeah? And so it's important that we have a good database which all the space debris particles to plan these maneuvers for the manned space flight. An important thing is to detect space debris actually. This can be done basically with 3 methods. You can use radar, or you can optical telescopes, or you can use lasers. We at the DLR use radar and optical telescopes, for example. Currently, we are working on a monitoring network. It's called SmartNet, which optical telescopes. Consists of 6 telescopes distributed over the world, which operates robotical, and they have optimized schedules for the telescopes. And the locations are like this, and then also in the southern hemisphere, so we can cover all the space around us. So, and then there's data that we get, like images like this, with space debris objects in the middle, and we have then do computations to do the object correlation to get the tracks and the orbits of the space debris particles. So this is the part where I'm not going into details. What I'm talking now about is a software for managing the overall database infrastructure and the computation of orbits and so on. It's called BACARDI. It's Backbone Catalog of Relational Debris Information. It's a database which should be complete. It should contain all the important space debris objects with high accuracy from sensors and from other operation data and from other third-party data sources. The science that we are doing is software side to build this kind of distributed database, and well, actually the space engineers are working on the computations for object correlation, orbit determination, propagation, object identification to identify what kind of particle is it actually, and for detections of maneuvers or further fragmentation of space debris particles. What happens from time to time is that the 2 space debris particles collide and split into many more particles. That we have to hopefully automatically find out what's happening and detect that. also the BACARDI system must have mission support. It must be used to provide orbit information, collision detection, re-entry prediction of particles, and this should be run in real time in Space Operations Center. I think this is the one that we run in Munich, in Germany, where the software will run at the end of this year. The overview of the system is, well, this is the very detailed system overview with all the parts that are important for the different computations and predictions. A more simplified view is this. We have a sensor network with optical, radar, and laser sensors. We have the BACARDI system with actually databases, user interface, and processes. And in the in the world of the aerospace engineer, processes are not really processes on a computer, but that are algorithms that run and compute something, like an orbit or a prediction of a collision or something like that. Those are processes. And we have the sensor scheduler below that controls the telescopes. We have connections to other users, so user groups, and we have additional external information. And the internal nodes, the processes, are very well. There are a lot of these things for orbit propagation, orbit determination, and so on and so on. And I'm not going into detail here. And another example is we have external data sources. This is one which you can actually try out, spacetrack.org. You can go there, register for an account, and get information about the orbit information about most of the satellites and other objects that are in space. In the screenshot, this is the ISS, International Space Station. It has the ID 25544, and at the bottom you can see, this is not working, at the bottom you can see the orbit information of the last orbit of the ISS, at the last trip around the Earth of the ISS. Made this screenshot this morning. This is actually data from this morning. So in the space, the system components of the BACARDI system are actually like a database, caching, processing, importing data, and we built a middleware around that. We call the middleware Skynet. I'm explaining that in a minute. And the processing is done with two ways, where the colleagues, the aerospace engineers, have like two kinds of processors. One half of that is Fortran code. The other half, the newer ones, are actually Python code. And also we have things like security and traceability for the system. And the basic middleware is called Skynet. The name is not actually very good, but it has some kind of a meaning, network for surveillance of the sky. So the name might change in the future, actually. And we didn't register like names on GitHub and so for that, because we are thinking about other names currently. But this is only the middleware that is hidden by the users that are using the system. The objectives of the middleware is using decentralized message queues for exchanging data between the different parts of the system. The middleware builds a scalable, self-organized network of processors and other stuff and databases with minimal network overhead. This is important, and it must be platform independent. So the production use in the Space Operations Center is on Linux, but the development is mostly in Windows and Mac OS. And we want to have provenance recording. And the technology decisions that we make for the first version currently is we based it on COMQ for the central decentralized network infrastructure and for the messaging. We use protocol buffers for serialization of data, and SQL Alchemy for database mapping. And especially zero-MQ and protocol buffers are really available on like many platforms and for many programming languages. And the different modules of Skynet are like network module, the data model module, the module process for processes, and the record module for provenance. The network module, as I said, is based on zero-MQ. I don't know if you haven't tried zero-MQ for things. It's a really cool library for basically a socket library for messaging. There's very few overhead. It's not based on a central broker, such as other like messaging libraries, but you can configure it in that way that it has a broker. It's really nice and flexible. It's multi-platform, multi-language, fast and small, and actually you can realize many connection patterns. It's configurable within like a configuration language. Well, actually these patterns are not from the Skynet system, these are just examples. And Skynet network, our network layer actually is based on zero-MQ. We have defined like a device as an abstract endpoint in zero-MQ, which is defined via the zero-MQ configuration language, ZDCF, zero-Q device configuration file. We do like automatically connect devices to each other if they fit. We support compression of large data package, serialization via protocol buffers, and the thing that we want to incorporate next year is encryption and signing of the data. And the network could look like that. So we have different devices like a broker or two brokers and a couple of worker nodes that do actually the computations and maybe database nodes and so on. And the layout of the graph changes from task to task actually. For the serialization, as I said, we use protocol buffers. This is also a nice technology that is very suited for applications where you have high performance constraints. It's specified by Google actually. Open source. It's similar to like what people are doing with XML for serializing structured data, efficient, extensible, and you have to define like your data structure in an interface definition language, in IDL. And in our model module of Skynet, we use the protocol buffer. All data models are defined as protocol buffer messages. We provide like basic data types for vectors and orbital data and so on, interfaces for caching. We do mapping to actual databases with SQL Alchemy, where we add like certain annotations to the protocol buffer messages. And we have special devices like for database connections. And the model definition in the Skynet is in a way that we are mapping protocol buffers to a database table, and we add like some kind of annotations to the protocol buffers. This is in this line here. This is in protocol. This is in protocol buffer interface definition file. We import like things for the database connection, and then you see for example, a definition of a vector, which is naturally very simple. So the Skynet model is actually very simple. We have a network message that we can send around, which contains of a header and different blocks of different chunks of data. The header contains the destination and the source within the network, and the different blocks can contain data from different databases or for different databases or commands or other things. And the model definition can be rather complicated. The model definition for orbital parameters and orbits is like, I I don't know, 3 or 4 pages on the screen. As you can see here, you can try to read this. And we have many models for other things that we have to compute. And to actually go from a protocol buffer definition to an actual database, this is really easy. You can just read the model definition and create a database structure. This is an SQL, just for an example, because it's the most easiest thing. But we support all databases that SQL Alchemy actually supports, and create a database table, and then we can work on the database in the distributed system. And the data access is also very simple. We can access the data while we can do regular queries on the databases, or we have like a database extension module defined in Skynet for an easy access to the data. For example, to get the orbital information for the ISS, you just make a call with the correct ID for the ISS. Actually, in practice, this is very simple, and the engineers are actually very pleased of this solution. So the next part of the Skynet is the process layer. This is an abstraction layer for the processes. As I said, Fortran codes or Python codes, or actually some of them are actually C codes. The integration is, well, I think classical. We can do like sub-processes with I/O via files or disk I/O or the name pipes. Or we can wrap Python or Fortran, we can wrap Fortran or C with Python to import it as a Python code, or we can write pure Python modules. And using that, we also use support like multiple processes, where we put one process on a single core or a single CPU. I'm not going into detail on this side. So the last part of the Skynet system is provenance recording. Provenance is some kind of metadata. This describes the process that leads to some piece of data actually. So as you can see, provenance is defined as a record that describes all people, institutions, entities, activities that are involved in producing a piece of data or a thing. That's the definition. And as you can see in the general picture, we have entities, for example, files or activities like processes or tools or software, or agents, for example, the humans that are steering a computation. And then we define the process that we have with some kind of a provenance model, and we can store actually, if you're running a process, we can store information about the running process in this data model. And what we're doing, this is like a standard from the W3C consortium, from the semantic web field. And what we are doing in Skynet is provenance recording. We record all activities during runtime. We can support multiple provenance stores. Provenance stores actually are Neo4j graph databases, because the provenance model itself is a graph, a direct acyclic graph, and we naturally use then a graph database for that. And provenance is important for traceability and provability of all data that we have in the system. So for backtracking of each produced data product, and for reproducibility of all products and all the data that we have generated. So a very nice technology. So coming to an end, what is the current state and the current work? Currently working on graphical user interface recognize that you haven't seen any graphical user interface. We have two versions, a web user interface based on Django, and we're working on a desktop version based on Qt and PyQt. And we are currently working on the workflow execution in the distributed network. And organizational topics that we're currently working on, without the workflows and without the web user interface, we currently provide an operational version to end of this year within our own organization. And besides that, we are working on an extended version with improved security and signing on and so on, especially for the German Army, for the Bundeswehr, which should be working there in 2017 or so. And we are also actually started working and using Skynet in other fields. For example, we have now started a project where we have to acquire data from a rocket motor, which is a rocket that actually starts. And we have to acquire the data during the start and then analyze the data so that the engineers can, watch and see what happens during launched rockets. And this will also, the activity have started. And for that, actually, we do have a clear deadline. This is nice in the software project. The rocket starts actually in May 2018. And in December 2017, we have to provide the software to the colleagues who prepare the rocket, and it must then, just work. And that's it, what I wanted to say. Thank you. If you have questions, you can ask me now or later. Otherwise, we can go to lunch. Yeah. Yeah.
The nature of this very important problem is that the number of collisions and the amount of debris in orbit increases non-linearly, which means that the items in your database will have to increase non-linearly.
Yes.
How do you keep the database from hitting its capacity under those circumstances? Is it easy to extend non-linearly?
Well, actually, we can. Currently we plan with a couple of millions of objects, which is really not too much in the field of database technology. And I think it's handleable. And what we're trying to do there is to federate multiple databases. We just not use one single database, but multiple databases. We can just add another database.
Add more databases.
Yeah. And the biggest problem is then the processing power, to query databases and use the data and process things with the data. I think that's the most important problem in that field. Oh, yes.
Could you shed some light on, just at a high level, the timeline, just taking the ISS, the recent near miss as an example?
Sorry?
Could you shed some light on the timeline in terms of the workflows? So looking at the ISS example and the data in BACARDI and processing things in Skynet, what was the timeline for that? Was it a few days out they were running models for what might possibly collide with the ISS?
Oh, there's a wide range of timelines for processing, from minutes to 2 weeks or even months. So in some cases, the incident 2 weeks ago, there was a timeline of about 3 or 4 weeks. So a couple of weeks before that, we know that there is a space debris object, and the colleagues in space can plan their work and then relaxed move to the Soyuz spaceship and wait and drink coffee and so on. And in other incidents, we have maybe only an hour or so. But actually, the system is planned that it observes the sky every time and do computations all the time around. And so we can predict. It means the different cases, if the space debris objects split into multiple objects, and we cannot really predict this for all cases, and we have to observe the sky and determine if an object is not present anymore, and is probably there are more, a couple of more now, and that's the reason why we have to do the processing all the time without any end, and hopefully we can predict incidents way ahead of when shit happens. Okay. Okay. So, yeah. Oh, yeah.
How fast can you run a query against a database and get relevant information back? Is it interactive, or do you have to have some sort of processing queue that people get put into, or how does that work?
Oh, you mean from if you're from the user perspective, it will be interactive. Yeah, that's a requirement, especially by the Army. Yeah. Okay, thanks. Lunch.